Good day. Our topic is all about determination of modulus of rupture of concrete beam. So first, let's determine what is modulus of rupture. Modulus of rupture is a measure of the tensile strength of concrete beam or slabs. Flexural strength identifies the amount of stress and force an unreinforced concrete slab, beam, or other structure can withstand such that it resists any bending failures. Modulus of rupture is also known as flexural strength, bend strength, or fracture strength. In short, ang modulus of rupture is yun na yung capacity, maximum capacity ng isang unreinforced beam or slabs na mag-resist ng tensile stress, or yun na yung kanyang maximum tensile strength. So next, standard test methods to determine the modulus of rupture of a beam. In order to test the flexural strength of a concrete beam, its span length should be at least 3 times the depth. The flexural strength is expressed as the modulus of rupture in PSI or in megapascal. There are two standard test methods to determine the flexural strength of a concrete beam. So by the way, para ma-determine natin ang modulus of rupture ng isang unreinforced beam is magkakandak tayo ng test. But before that, dapat i-make sure natin na yung span ng ating beam is 3 times niya yung depth niya, yung kapal. 3 times ng length yung kapal ng ating beam. So, let's proceed sa testing methods. So, una is center point loading test. In this test method, the entire load is applied at the center of the beam's span length. Here, the flexural strength or modulus of rupture is higher than the modulus of rupture of the third point loading test. The maximum stress is present only at the center of the beam. So, ang unang method is center point loading test. So, maglalagay tayo ng load sa gitna ng ating unreinforced beam, and then ititest natin ito, and i-determine natin kung saan or kung anong loading nag-fail yung ating beam, or kung anong load siya nag-fail, and magagamit natin yung data na yon at isa-substitute natin siya sa formula na i-explain sa atin later ng reporter number 2. So next, let's proceed to the second method, the third point loading test. So in this test method, half the load is applied at each third of the beam span length. Here, the flexural strength or modulus of rupture is lower than that of the modulus of rupture found in the center point loading test. In this test, the maximum stress is present over the center 1/3 portion of the beam. So dito sa third point loading test is maglalagay tayo ng dalawang load sa ating beam na ang location niya is sa every 1/3 ng ating beam. So maglalagay tayo ng dalawang load na kalahating load kumpara doon sa center point loading test. Kung sa center point loading test is load F, dito sa third point loading test is F all over 2. So ganun pa rin yung gagawin natin. I-determine natin kung anong loading nag-fail or ilang load nag-fail yung ating beam, and magagamit natin yung data na yon para isa-substitute natin sa formula para malaman natin and makompute natin yung modulus of rupture ng ating beam.
I am Rajiv K. Kasid and this is my report.
The test is usually conducted in rectangular beams. These beams are applied into two roller supports and the applied load is placed in the middle of the beams. So, yung formula ng 3-point bending is ito. So, ipapakita ko sa inyo kung paano nakuha itong formula na to.
Magsimula tayo sa ganitong beam.
Na mayroong dalawang ruler support at yung applied force niya is nasa gitna. So, kapag nikat natin yung beam sa section AB, may lalabas dyan na moment at shear. Para makuha yung moment at shear natin is sa summation force vertical tayo para sa shear. At eto na siya, guys. And then kapag naman para naman makuha natin yung moment dun sa cutting section natin is magmo-moment tayo. At ito na yung nakuha nating moment dun sa cutting section natin. And then sunod naman, pag nikat natin yung beam natin sa section ABC, pag nikat natin yung beam natin sa section A, B, and C, lalabas din dyan yung moment at shear natin. So, para makuha yung moment dyan or yung shear dyan is magsa-summation of force vertical din ulit tayo. So, ito na yung nakuha natin dyan na shear. Kagaya lang din dun sa kanina, kaso lang yung sa section AB is positive yung shear niya. And then sa section ABC naman is negative na yung shear niya. So, para naman makuha yung moment natin is magsa-summation of moment din tayo kagaya ng kanina sa section AB. So, ito na yung moment dito sa section ABC. So, kapag ni-draw natin yung shear and moment diagram nito, ito na yung magiging kalabasan niya.
Using the bending stress equation,
Which is the stress is equals to moment times distance all over area moment inertia. So, we can calculate the maximum stress of the beam by inserting the value of the maximum moment and the distance from the neutral axis and the area moment of inertia about the z-axis. So the problem is we don't have the value of the y and I yet. So to get the value of y, we will look at the z and y axis of the beam. So this is the y and z axis of the beam. So this is z and this is y, and we have base here, and then this is the height. So we can see that there is a base and height. So the neutral axis of the beam is placed in the half of the height of the beam in the z-axis. So the value of the value of Ry is 1/2 of the height. So meron na tayong value ng y. So sunod naman is yung value ng I natin. Ito. So para makuha yung value ng I natin is we just put the formula of area moment of inertia about z-axis. Yung formula na yun is ito siya. 12 base times height to the third power. So yan. Meron na tayong value ng I. So by substitution in the formula, so ang value ng maximum moment natin is 1/4 FL, and then the value of the y, which is the 1/2 times height, all over the area moment of inertia natin, yung value niya is 1/12, 1 over 12 base times height to the third power. So yan. So by simplifying it, we can makukuha natin is 3 FL all over 2V times height. Yan. So yan yung formula ng 3-point bending. Or we can replace the variable according dun sa formula or according dun sa PowerPoint natin. So this is ganito yun. 3FL D all over 2BD squared. So yan na ngayon yung formula natin. Try to solve a problem using 3-point bending test. So this is the problem. Compute the maximum flexural compressive stress and flexural tensile stress in the beam. Use the cross section as 300 mm by 200 mm. So this is the beam. We have here applied load 200 kilonewton. So this is the y and x axis, and then this is the cross section of the beam, which is the y and z axis. So as you can see, our beam is symmetrical. If we draw the moment diagram of our beam, we will get a positive bending. So our beam would behave like this. Ganyan, magiging ganyan siya. Ganyan. So, dyan sa taas, dito sa taas, dito natin makikita yung compressive stress. Yan, yung compressive bending stress. Bali, dito naman sa baba, dito natin makikita yung tensile bending stress. Dito. Pero kapag yung moment diagram naman natin, or yung moment yung moment diagram natin is negative or bending or negative bending siya, ganito na naman magiging itsura nun. Ganyan. Ganyan. Dito naman yung compressive. Diyan. And then dito yung tensile. Yan. So, therefore, titingnan naman natin yung y and z axis ng beam natin. So, let's analyze this. Since meron tayong positive bending, sa baba, meron dyan natin ilalagay yung tensile, or dyan natin mahanap yung tensile stress natin. Tapos dito naman sa neutral axis natin, 0 yung stress dyan. And then sa taas naman, meron dyang compressive bending stress. So yan siya. So yan, dito yung tensile, and then dito naman yung compressive. So para ma-solve natin ito, we need to locate the distance of our compressive and tensile stress to the neutral axis. So kailangan natin malaman ito, yung distance nito. So yan. So di ba alam naman natin yung pagkuha ng distance ng neutral axis, di ba? Kalahati lang siya ng original height ng beam natin sa may z-axis. So, dito siya. So, pag ni-divide natin yung 300 by 2, magiging 150 mm siya. And 150 rin dito. So, yun na. So, let's solve it using the formula na na-derive natin kanina. Dun sa 3-point bending test. Anong ayun? Ito yun siya, di ba? Stress is equals to 3 times F L all over 2 B H squared. So, yan, di ba? So, mapapansin natin, meron tayo lahat given, meron tayo lahat value. Meron tayong value ng force, meron tayong value ng original length, base, pati height. So, ang gagawin lang natin is i-substitute natin yung mga value natin. So, i-substitute na natin. 3. So, ano yung value ng force natin? So, naka kilonewton siya. So, i-convert natin siya sa newton. So, para ma-convert siya, i-multiply lang natin siya ng 1,000 newton. So, 200 times 1,000. Tapos, yung original length, pag ni-add natin itong dalawa, magiging 4,000 mm siya. 4,000 mm. Divide siya sa 2. Meron tayo, ano yung base natin? Yung base natin is 200 mm. 200 mm. And then yung distance natin, yung original distance natin dito. Di ba 300 yan? 300 squared. So, pag ni-calculate natin yan siya, 3 times 200 times 1,000 times 4,000 times 200 times 300 squared. Yan ngayon ang compressive bending stress natin. Yan. Equal din ito siya sa tensile stress natin. Since symmetrical yung beam natin, equal lang siya doon sa compressive and tensile stress natin. Ay wait, nakalimutan ko yung unit pala natin. Ang unit natin is Newton millimeter squared. Newton millimeter squared. Yan yung unit ng stress natin.
So next is
4-point bending setup where the loading span is 1/3 of the support span. Just like 3-point bending test, it is usually conducted in a rectangular beam with 2 roller supports. But unlike the 3-point bending test, 4-point bending test has 2 loadings. So this is the formula of 4-point bending setup where the loading span is 1/3 of the support span. Sa inyo kung paano kunin yung formula ng 4-point bending setup where the loading span is 1/3 of the support span. So nakikita nyo yung beam natin is dalawa yung applied load nya. So ang magagamit nating pang test dito is 4-point bending test. So so ito na siya. Para makuha natin yung formula is kagaya nung sa 3-point bending test, magka-cut din tayo ng mga sections. So una is ika-cut natin itong section AB. So kapag na-cut natin yung section AB is lalabas na yung moment dyan. Yung moment, pati yung shear. So, mag-moment tayo. So, para makuha natin yung shear dyan, mag-summation of force vertical tayo para makuha natin yung shear dyan. So, ito na. Makuha natin. So, ito na yung shear nya dyan. 1/2 times F. So, para makuha na naman yung F, ay yung moment sa section AB, magmo-moment din tayo. So, ito na. Ito na yung nakuha nating moment dyan. Then, sunod naman is, magkakat tayo ulit sa section ABC. So, kapag nakat natin sila, ito na yung magiging figure natin. Ito. So, meron din dyan moment pati shear. So, kagaya nung sa una, ganun pa rin, mag-summation of force vertical tayo para makuha yung shear dyan. So, dito, yung shear na nakuha natin dito is 0. And then, yung moment naman na nakuha natin dito is ito na. Then, last, magkakat ulit tayo sa A, B, C, and then D. Dyan sa section na yan. So, ito na. Ito na yung figure natin. So, ang nakuha nating shear dyan is ito. Negative siya. Kagaya lang din dun sa section AB. Kaso nga lang, ito positive. Ito naman negative. So, ang moment na nakuha natin dito is ito. Ito siya. So, kapag ito, pag ginawa natin ito ng shear and moment diagram, ito na yung magiging labasan niya. Yan. So, ito. So, meron tayong ang maximum moment natin dito is ito. So, kagaya ng kanina, gagamitin ulit natin yung bending stress equation, which is the stress is equals to moment times distance all over area moment of inertia. So, may value tayo ng maximum moment. Anong value ng maximum moment natin kanina? Yung nasa figure natin, which is ito. So, ang moment natin dyan, ang maximum moment natin is FL all over 6. And then, ang value naman ng distance natin, distance from neutral axis is 1/2, diba? 1/2. Kasi beam din siya, rectangular. 1/2. And then, ang I naman natin, or yung area moment of inertia, is, yun lang din, yung formula niya, which is the 1 all over 12 times base times height to the third power. Yan. So isa-substitute natin yung mga value na yan. So, ito na siya. So, FL over 6 times 1/2 is height all over 1 all over 12 base times height power. So, yan. So, kapag sinimplify mo ito siya, ito na magiging kalabasan yan. Ito na. FL P yan. Square. So, yan na yung formula niya. So pero kung susundin natin yung variables dun sa PowerPoint natin, pwede natin siyang palitan. So, gagawin natin ganito. P, D. Yan. Papalitan lang natin yung letter H ng letter D. So, yan. Ito na yung formula. Pwede naman ito, pwede rin ito.